Welcome everybody to lecture 7, which is on optimization. So we're going to continue talking about finding different points along functions today, particularly looking for optima. So just as a review, by this point, you should feel relatively good with open methods, and particularly the fixed point method, Newton-Raphson, secant method, and inverse quadrature. This is all going to set us up for today and the rest of the semester. So we had previously talked about finding roots, right, where the function was equal to 0. Now we want to look at the other major portion of engineering function-based methods, where we want to find not where the function crosses 0, but where a function is a maximum or a minimum. This is critical because in many engineering applications, particularly in chemical engineering, we want to find some sort of system or way to run a system that has the best performance. And that best performance can usually either occurs when a function is at a maximum or a minimum. For example, we may want to know when conversion in a chemical process gives us is the highest, or when the cost of running a process is the least, so a minimum. There's several ways that we're going to talk about doing this. This is just a very brief introduction, so we'll cover derivative roots, golden section search methods, and parabolic interpolation. We're going to look at this only in 2 dimensions, but there's a whole world of extrema finding methodology. If you're very interested, we can go into it in office hours. Okay, so let's start with what is a maxima or a minima. So just to get us in that field. So a maximum or a minimum is the point in the function which is the largest on that set, so that would be a maximum, or is the smallest value. And optimization is our process of finding either the maximum or the minimum. Once again, this is going to be particularly important when we're looking for processes or situations that are effective as possible, or where an event is most likely to occur, or something is least likely to occur. And so optimization mathematically is finding where that function is a maximum or a minimum. There are several types of maxima and minima. So maxima, plural, minima, plural, minimum, a single, maximum or minimum. So we can either have something called the global maximum, shown here, which is the largest point over the entire space X, and we can also have a local maximum, say this point shown in white, which is the largest value of the points around it, so say in between those 2 red lines. However, it's still lower than the global maximum. We're going to have the same effects when we talk about minima. We can have a global minimum shown here, where it's the lowest point on that entire function, and we can have a local minimum, which is the lowest point if I go to the left or the right before a maxima, and is only locally that minimum. Ideally, we want to find, ideally we would like to find the global maximum and minimum, but as we're going to see, our methods are going to only help us find the local maximum and minimum. Okay, so let's start describing mathematically what is an extrema, or maximum or minimum. Excuse me. So these extrema of these functions are going to occur when our derivative of our function is equal to 0. Right, so if I'm sitting at this global maximum, my first derivative is equal to 0. If I'm sitting at the global minimum, my first derivative is equal to 0. And then we can say the same thing at the local set. So we can now define mathematically maxima and minima are. We can further differentiate between maxima and minima by looking at the second derivative, where a maxima is going to occur when the second derivative is negative. Let me put that in here. If our second derivative is less than 0, and our minima is going to occur when that second derivative is greater than 0. Okay, and so I could write these out for the local maxima and minima as well, because it holds at those two locations as well. So now we have these definitions of what is an extrema, or what is our maximum and minimum. They're locations where my first derivative is equal to 0, and then we can differentiate between a maximum and a minimum by looking at that second derivative, and particularly the sign of that second derivative. So this is good to know, and it's going to set us up for mathematically looking at these 2 points. But how are we going to implement this? How are we going to use this definition to determine what that where that maxima or minima is occurring, and then what that value of that function is? And so the easiest way to think about this is to think about that derivative definition. We said on the previous slide that the location of our maxima or minima is going to occur when our derivative is 0. We've just spent an entire 2 chapters looking, understanding how to find the location where a derivative is 0. Therefore, the most direct way to find a maxima and minima is to convert a function and find the location where where its derivative is 0. So let's take this function f of x. So say 5x squared times exp negative x, which I've drawn out on the right here, where here we have f of x. We can see that as I go from 0 and increase x, we see this increase, a maximum that's going to occur roughly around this x equals 2 point, and then curtail off. We know that that maximum is going to occur where f of x prime is equal to 0. Therefore, what we need to do, or what we can do, is convert f into a new function g of x. That's the derivative. All I've done is moving from f to g is I've taken that derivative. So the derivative of f of x dx, we can do this out together, is 10x times exp negative x minus 5x squared exp negative x. Okay, so if I plot out that function, we'll see, as expected, that the maximum of f of x occurs where g of x is equal to 0, right? Therefore, all we need to do is set g of x equal to 0, and then use the root finding methods that we've previously talked about. So this could be anything like Newton-Raphson, bisection, false position. Any of those methods can be used to find x where g of x is 0, which will then let us know where that maximum is. In order to find the Therefore, there are 3 steps to using the derivative roots formula of finding maxima or minima. Step 1, we take the derivative of f of x to get g of x equal to f prime of x, and we set g of x equal to 0. Then in step 2, we use a root finding method to find x such that g of x equals 0. I'm not going to go into that root finding method at this point because we spent a long time on that in chapters 5 and 6, but all those methods are going to apply. After we found what that root is, we can now do step 3, which is plug x into f of x to get the extrema, or the extremum, because it's going to be at a single location. What you'll notice through this step, particularly in step 1, is we have to be able to take that derivative. We need to know what the derivative of that function is. So we could use something like the secant method to calculate an approximate derivative, but that still requires then lots of function evaluations. So we want to come up with a different method that's going to require only the values that we have with f of x. So once again, if we know the derivative, we can use root finding methods. But if we don't know the derivative, or there's no easy way to calculate g of x, we want to use a different method. So the first method that you might be thinking about is bisection, right? That's where we started. It was relatively efficient with a root finding, but it's going to end up not being so effective in maxima location. But let's just take ourselves through this example and prove to ourselves why bisection may not be the most simple way of finding an extreme. So let's say, let me make sure that I have a good color here, maybe red. So let's say we have this function, once again, f of x, here's x, and we want to use bisection or bisection-like method to find that maxima. We can start just like the bisection method by guessing two values, let's say 1 and 5. In the bisection method, we would take the average, or the middle of those two guesses, right, and go up top and look to see which side crosses 0. However, the problem is, if we only use these 3 points, we don't know whether the extreme is on this left side or on the right side. Right? We just don't have enough information using bisection. What we need is a 4th point. Right? So with only 3 points, there's no easy way to tell which side of bisection the extrema is on. So we need to move to a new method. So let's say instead we take a guess, maybe once again at 1, maybe this time at 4, and I'm going to guess a 4th point. So here I have 3, and here I have 2. Now I have 3 points on which to operate. Now, 4 points at which to evaluate. So now I know that by looking at the relative values of these 4 functions, that the extrema must be sitting in this regime, right? Maybe pick a better color. That the extrema must be sitting somewhere between 1 and 3, because we have a value that's higher between 1 and 3, rather than sitting between 2 and 4. Because if I look at this value, 3 is going to be sitting lower than the value at x equals 2. So we know that the maximum must be between 1 and 3. So therefore, I could get rid of 0.4. I could now set a new sort of x lower, x upper, and then divide, say, divide this into quarters once again, right? And then I can do this process repeatedly. However, what you'll notice, or maybe I'll write out this sort of idea. So cut the search range into quarters. We then checked the interior points for which was higher. Then we eliminated one of the outer points that's on the side of the lower value of the interior points. Right? So we can then, this then gives us two new points, so say 1 and 3, and we're ready to start that process again. And we can do this iteratively, just like we did with bisection method. Now, the problem with this is this can be very expensive, right? I had to calculate not only points 1 and 0.4, and then 2 and 3, but when I move on to the next step, I need to recalculate these two new points that are going to divide us into quarters. If my function evaluation is relatively fast, it doesn't matter so much, right? That I'm doing all these function evaluations. So if I'm 1 line or 2 lines of code, not so expensive. But this gets very expensive, computationally expensive, if it takes a long time to calculate f of x. So for example, in some of my own research, when we're doing these optimizations, the calculations of this f of x function can take an hour for each step. So that means just to get those 2 interior points, it would take 2 hours, right? So we would end up waiting a very long time for each successive step. So ideally, we'd like something that moves a little bit faster so that we can save some of this information. If you remember when we were going through the algorithm on the right-hand side, we had already calculated this point at x equals 2, and then we threw it immediately out. There has to be a way that we can keep some of that information by cleverly picking how we look at those interior points. And that idea of clever picking is called our golden section search. The golden section search is interesting because of this ratio that we're going to use. So if you remember from maybe an art class or an art history class, there was a lot of interest throughout history and in art of looking at the golden ratio. And the golden ratio is this rule that says L1 plus L2 over L1 is equal to the ratio of L1 over L2, right? So if I look at the whole length of this line and I look at its proportion of the whole to just L1, the proportion is the same as L1 is to L2. Nature comes up with this lots of times in terms of spirals, so if you think of conch shells, and then shows up in a lot of mathematics. This ratio is going to help us. So this ratio of L1 plus L2 over L1 equals L1 over L2 is called the golden ratio. And this is going to be symbolized by the letter phi, which is equal to roughly 1.618. There's a lot of extra digits with this, but for our intents and purposes, we'll stick here. Why this is important is because as I cut this in half, or as I cut this along this line, my distance from here to here is going to now be my distance from one side to the other side when I cut this, when I bisect this or cut it into quarters again. So we're going to be able to, as I start doing my algorithm, looking for which side of which position my maximum must lie between, I can start saving points. All right. So what this is in essence going to do is it's going to reduce the number of points that we have to evaluate our function at, as long as we use this ratio in determining where we need to bisect our segment. Let's put this into practice. So remember, the goal is going to be, let's spell that right. Our goal is going to be finding in a set of interior points that we get to keep from one iteration to the next. Keep at I plus 1, and do so in the most efficient way as possible. So what we mean is we're going to pick a lower estimate, pick an upper estimate, and then find some set of interior points, maybe here and here, that will make this actually a little bit even, that are going to be keepable from one point to the next and maintain a constant stretch. So maybe we have a point here, and then maybe we have a point here at number 4. And it turns out that this is going to be most efficient when this first width is in a ratio of 2 minus phi to 2 phi minus 3 to 2 minus phi. Right? So we can take these restrictions and put some numbers to it. So we're going to call our first point x1 to be xl plus d. So this is going to be xl plus d. And we can have our second point be xu minus d, where d is phi minus 1 times ux minus, times xu minus xl. And so these three equations for our green point and our red point are coming from fitting those ratios. So I'm going to call this point at roughly 4. It's going to be called x1, and I have that in red, x1, and then this point down here is x2. We're going to stick with these definitions of x1 and x2 because that's what's in the book, and I don't want to confuse you, even though it may be a little more satisfying to have the numbers flipped a little bit, but we're going to stick with our book's convention. Okay, let me clear this up just a little bit And then we can go through a hypothetical practice. So let's look at our individual steps. So step 1, we calculate x1 and x2. Step 2, we're going to determine the triplet set that contains our maximum. This would work for the minimum too. So what I mean by determine the triplet set. So we're going to look at, first we'll look at XL, X2, and X1. So this set, and we can estimate the maximum from the green set by looking at that interior point. Next, we can look at the maximum for the right-hand set. Maybe we'll do this one in red. And we can estimate its maximum by the function value at x1. Okay, so in essence, we're asking ourselves, is f of x2 bigger than f of x1? Right? So if f of x2, so this point right here, is bigger than the point f of x1, we know that the maximum must lie on this first set. So we can go in and we can now update. Let me switch back to green. We can update our guessed bounds. So what this means is we're going to get rid of this xu and this x1, and that x1 becomes our x upper bounds. So now we're ready to calculate a new x1. And you'll notice that this is picked very carefully so that this x2 is still going to remain x2, right? So I'm going to draw in a new, say, xl or x1, and we get to keep xl, x2, and xu. We don't have to reevaluate those functions. Okay, and we can do this repeatedly, just like we did before with the bisection method, choosing, always looking between f of x2 or f at x1, and determining which side, whether to lose the lower bounds or the upper bounds. So in essence, by using the golden search ratio, we only need to compute one new function evaluation per cycle, right? Because I've ended up keeping one of my x's every single time. Yeah, sorry, both of the old x1 and x2s are kept every single time. How we're going to determine when to stop this cycle is going to be once again dependent on our approximate error. The formulation of the approximate error is a little bit more in depth this time, but it's going to follow that same idea that we talked about with bisection and false position. In this case, our approximate error is going to be 2 minus phi times the absolute value of my upper value minus my lower value divided by t opt times 100%. So let's go in and remember what each of these pieces are going to be. We have our x lower, x upper, and this x opt piece is going to be our best estimate for the optimum. So that's either going to be x2 or x1, depending on which one is higher. Just like before, we can calculate the estimated error every single step, and we should see this contract over time and use this as our stopping criteria. Let's put some numbers to this, though. So we're going to take a function, f of x equals x squared divided by 10 minus 2 sine x, and this time we're going to find a minimum. Finding the minimum is going to be exactly like finding the maximum, but instead of looking for those interior points that give the highest value, we're going to look for the case where it's the lowest value. So let's start out, we need to start out by guessing a set of interior and exterior points. So let's say start out with case 1. We're going to guess, maybe we don't know what that first point is, so we can guess 0. I can stick fx equals 0, gives me 0 squared divided by 10 minus 2 times sine of 0. This is going to be 0. I then guess an upper value. Let's just say I'm going to guess 4. I can then evaluate f of 4, which is going to be 4 squared over 10 minus 2 times sine of 4. This is going to come out to be, when you plug it all in, roughly 3.11. So I'm going to just put that into my table, 0.11. Now I need to know what d is. If you remember from the previous slide, we have d equals phi minus 1 times x upper minus x lower. This is going to be, once again, 1.618 minus 1 times our upper value, in this case is 4, minus the lower value of 0. I can do all of these, all the math out, and when I do, I end up getting 2.4721. So I can put that in my table right here, 2.4721. Now I'm ready to calculate my x1 and x2. So we're going to go back to our definition of what x1 is. In this case, x1 is xl, make it capital, plus d. So that's 0 plus 2.4721. Oh, well, that's relatively easy. We have just 2.4721. I can plug that into my function, 2.4721 equals 2.4721 squared over 10 minus 2 sine of 2.4721. I'm sort of running out of room, so I'm just going to put that into the table. That ends up being negative 0.6, whoops, negative 0.63. Okay. And I can do the same thing for my x2 point, which is x upper minus d. So we have 4 minus 2.4721. That, of course, is 1.5279. And then I can punch this number in to my f equation. I'm not going to go through the math here, but this is negative 1.764. Okay, so now I have all of my 4 numbers that I want to look at. I'm going to just erase some of this math so that we have some more space to work. So we want to look at the sets of triplets. So we want to look at our first set of triplets, which is maybe triplet 1, which is x lower, x2, x1. So we can put the function values in here, 0, negative 1.76, and then x1 was 2.47. And we can look at our second triplet set, T2, which is x2, x1, x upper. Once again, this is negative 1.76, 2.47, and then finally for f of x upper, that's 3.11. So if I look at these two sets, which one's going to contain the minimum? If I sort of plot this out, I see that this is going down. If I plot the first triplet, I see I start at 0, I go down to negative territory, and I come back. Right? So this x2 is going to contain the minimum, right? x2, negative 7.16, is lower than this 2.47. So this triplet set, the left triplet set, is going to contain our that minimum. So when I move on to step 2, I'm going to retain XL. I'll retain its value. Oops, maybe I'll switch color here. I'm going to exchange this X upper. That didn't show up very well. I'm going to exchange my upper X value for X1. This X1 is now going to become, what was X1 is now going to become my XU. So I'm going to take this, plop its values into X upper. So now I have an upper guess of 24721, and I can drag the value of negative 0.63. Oops, I guess I should correct this. This is negative 0.63. Negative 0.63. There we go. So now I'm ready to calculate D. We can once again use the equation that D is equal to phi minus 1 times X upper minus X lower. I can go into my table. That ends up being 0.618 times 2.4721 minus 0, which is 1.5279. So we can put that into our table, 1.5279, and then we're ready to calculate x1 and x2. So for just now, we'll calculate this out, but you'll see the pattern in a second. So x1 is our xl plus d, right? xl is 0 plus 1.5279 is 1.5279. Well, what do we immediately notice? That's the exact value as x2, right? That idea that we were talking about earlier is showing up again. We're getting to keep one of our numbers. So we can plug in our 1.5279. We can calculate pull down its value here. So we really only need to calculate x2. So here I'm going to just erase so that I have some space. We can calculate x2 equals xu minus d. We have xu, that's 2.4721, minus d, which is 1.5279. This is going to all come out to be 0.9443. So we can plug that into this value, 0.9443, and find the appropriate x value that's negative 1.531. Okay, so we can now do this. Again, we can look at our triplet sets. I'm going to erase this. Now, instead of writing out the triplets, let's just look at those x1 and x2 values. F of x1 is negative 1.762. F of x2 equals negative 531. 1.531. So we can immediately see that x1 this time is the value that's lowest. So maybe I'll switch colors again. Maybe orange. So this x1, so this x1 is now containing what we want to keep. So we're essentially going to now move, this time, our x2 to be our lower value. Okay, so we can plug this in. We've now got 0.94. We can pull out that x2 f of x value, negative 1.531. Our upper value we're going to keep, so that's still 2.47 with its negative 0.63. And we now go to x1. Which we're going to need to calculate. So x1, we're going to calculate using xl plus d. We need to calculate a d here. Using that formula, we have 0.944. And that gives us now an x1 of 1.88. We can punch that number in and get negative 1.54. And then we get to keep our x2 from that old x1. So that's 1.529. We get to keep its associated 1.72. Okay. And we can keep doing this again and again and again. I encourage you to take the next steps and see how it converges. With that, let's switch to a new type of method. Let's now consider a different approach than, say, the bisection method took. The next step out of that was to move to the false position method, where we tried to fit a line between 2 points. So let's think about whether we could use sort of a similar approach to finding a maximum or minimum. Let's say, for example, that we were sitting at, say, 0.75 and 5. We could take a similar approach to the false position method and say draw a straight line between these 2 points. However, if we did that, we wouldn't really gain much more information, right? There's no maximum along a straight line. If, however, we take this example function and we look at the area around the maximum, so say in this area, we can say that it resembles another shape, another low-dimensional shape. This time, instead of starts looking like a parabola. So if I just draw sort of a parabola, we can see that we get a sort of paraboloid fit. So maybe instead of false position method, we could fit a parabola to several points on this surface and then take the position, the maxima of or minima of the parabola as our next guess for the fit of the curve. And so this is called parabolic interpolation. Take this shape so you can see the outline of the shape in black, where we see the true maximum, and we're going to take 3 points along that function. We need 3 because 3 points is the minimum required to fit a parabola. Once we have these 3 points highlighted in as these white dots, so 1, 2, 3, we now have enough points to fit a parabola. And if we have any 3 points, we can fit a parabola. So then what we're going to do is we're going to fit that parabola, then we're going to find the maximum of that parabola, and then we're going to use this as our next point. So in essence, there's going to be 2 different steps. So first, step 1 is fit a parabola. To this equation, y equals ax squared plus bx plus c. I'm not going to go into the details of fitting this parabola, as we're going to get into that in the next chapter, and the math gets a little bit nasty, but what you'll end up having is some sort of equation where a is a function of is maybe h of x1, x2. It's, 3 points and the associated f of x values. We can fit a, b, and c to that function. So once we have a paraboloid fit, we want to find the max. So to do this, we use the fact that maximum, or once again, minimum, are going to occur at that first derivative. So we need to find out what y prime is. In this case, b. We're able to rearrange this equation, and we want to set this equal to 0, We want to set this equal to 0 so that we can then find where that maximum of that parabola is. Right? So if we do rearrange this, we can find that that maximum is going to be at from this fit, punch it in to this x equation, and that will then give us the next x. So we eventually have this this. So I've gone and done this all out for you, taken all the numbers and plugged them in, and we end up with our final form of this equation. So this equation down here is going to give us the maximum, x4, or the minimum, for any set of 3 points on a curve. Right? So just as before, we're going to get this x4, and then we the function with the x value, that's the lowest value. So in this case, looking at this example, we would start out with positions x1, x2, x3. So those are guesses. Going to go and drop that lowest case, x4. That x4 would sit right here when we put that value in. This would become our new x1, x2. And then that one stays x3. Okay. And so we're going to go, then we can fit the parabola again. Find the max, so either x1 or x3 should be discarded, and refine, as we're hopefully getting used to by now. Good. So let's take this and let's put this into practice. We're going to use the same function that we used with our previous examples in order to see how the parabolic function is going to, how the parabolic interpolation is going to work. So once again, we're going to use this f equals x squared divided by 10 minus 2 sine x. So the first thing that we need to do is come up with a series of estimates. So let's pick 0 as an x1 and 4 as an x3. Right? Possibly plotting this out earlier would then give you an idea of where that minimum is. So now we need to go in and we need to calculate what f of 1 is. Sorry, f of x1, which is, of course, f of 0. So if I plug 0 in, I've got 0 squared over 10 minus 2 sine of 0. This is going to be 0. So I can put that down here with f of x2. In this case, x2 is 1, so I have 1 squared divided by 10 minus 2 times the sine of 1. This is going to come out to be negative 1.5829. And then finally for x3, we have 4 squared over 10 minus, which is 3.1136. We can go ahead and enter these values into our table just to keep, and now we're ready to do our interpolation. So we're going to, from the previous slide, to estimate what x4 is. So I'm just going to write that up here. x2 minus 1/2 the quantity the quantity x2 minus x1 squared times the quantity f of x2 minus f of x3 minus x2 minus x3 squared. Ran out of space times f of x2 minus by here. Then on the bottom, we have x2 minus x times f of x2 minus f of x3 minus x2 minus x3 times the quantity f of x2 minus f of x1. Okay, so big long equation, but we know all of these little pieces. So I'm going to erase some of this earlier math as we're going through these iterations. Okay, so let's start in. So we've got x4 equals x2. I'm going to come down to my x2 column. This is what's called for. So we have 1 minus 1/2. On top we have x2 minus x1. So x2 is 1 minus 0 squared times f of x2. F of x2 is negative 1.5829 minus f of x3, which is 3.1136, minus x2, so once again 1, minus x3, 4, which is 4. We're going to square that. Now we're going to look at the f of x2. So that's once again negative 1.5829 minus f of x1, which is 0. Okay, so that rounds out the top half of that equation. Now we're going to go into the bottom. So we have x2, 1, minus x1, which is 0, not squared. Sorry about that. Times the quantity, this is 0, times the quantity f of x2 minus f of x3, so that's the same as the top, f of x2 minus f of x3, minus x2 minus x3, x2 is 1 minus 4, no squares, times the quantity f of x2, so that's negative 1.5829 minus f of x1 is 0. Okay. So all I've done is I've taken this equation that's in the upper right-hand side and then plugged it in down here with x4 equaling 1.5055. Okay, so I can put that in my table now. 15055. Right? And then just for completeness, we can take f of x4, plug that squared, divide by sine 1.5055, and this equals negative 1.7691. So we can put that in our table, negative 1.7691. Okay, so now we need to look at this now that we have our estimate for what our new minimum is, we need to figure out which point I need to drop. Do I need to drop x1 or x3? So let's look at the values that we have right now. So I'm going to pull out the x1, which was at 0, x2 is at 1, x4, because this is going to be in between, so this is 1.505, x3 is at 4. All right, so now I've lined these values up so I have a better understanding of where I'm going. So now I can write out the f of x values. So we have 0, negative 1.58, not sure why I added that in there, negative 1.58, negative 1.76, and then 3.1136. Now, this value, this f of x value, is showing us that we have a lower value that's sitting between x2 and x3, right? This x4 is between these two values, and the value is lower. So this must mean that the shape of the curve looks sort of like this. Because the minimum is between x2 and x3, we want to preserve those 2 points. We want to get rid of x1. So maybe we can draw. We want to get rid of this x1. So we're now going to shift these points over and make our new x2, 4, x2, 3, and 4. So in the second iteration, we'll maybe call 2, I can go through and set x2 to be our new x1. So I'm going to pull this down, so 1. We can preserve that negative 1.58 from the previous round. x4 is going to fit in there next, so we can go 1.505, and we can preserve its negative 1.7691. Now comes x3, which is just going to stay x3, so that's 4 and 3.1136. And we're ready to punch in all of these numbers again. So let me just clean up the screen a little bit, and then we can go ahead and calculate x4 again. So now that we have a clean slate, we're ready to start again. I've rewritten out that x4 equation in a little bit larger space so that we can follow along a little bit better. So we're now ready for my second iteration. So we're going to use this column, this row, and we're just going to now plug in all the numbers as they come along. So x4 is going to be x2. This time x2 is that 1.505 minus 1/2. We have x2, 1.505 minus x1, which is 1 squared. Now I'm going to go look in these secondary columns for my f of x's. So first we have f of x2, which is negative 1.7691, minus f of x3, which is 3.1136, minus x2, 1.505, minus x3, which is 4. Now I'm going to take once again, those quantities of f of x2. Okay, I'm looking at the quantity here, negative 1.7691 minus f of x3, which is 3.1136. And that completes that top row. And I'm going to go ahead and go do the bottom row. That's 1.505 minus 1, not squared. Negative 1.7691 minus 3.1136 minus 1.505 minus 4 times minus 1.7691 minus 3.1136. And I can do all of this out, and we end up getting 1.4903. You can immediately see, as I put this down here, that this value is quite close to our first guess, right? Before, with the golden search method, it took several iterations before we started converging. And we're already there on my second, on that second iteration. This is because we're using a lot more information about the local topography of my function to get to this solution. Right? And so we can put in that f of x4. I'm not going to do out all the math, but this time we get negative 1.76. I'm sorry, 1.7714. Right? So in the second round, we're already matching the error between these two rounds is out in that hundredths or thousandths place, right? So we're getting there very, very fast. So now we once again want to decide whether I want to drop x1 or I want to drop x4. So let's draw out sort of our lines here. So we can say x1 has a value of 1 and a value of negative 1.58. If I go next to my number line, I have x4, which is occurring at 1.49 and a value of negative 1.77. Now comes x2, 1.505 with a value of negative 1.769, and then finally x3, which was sitting at 4 and had a value of 3.1136. So we can see instantly that x4, maybe I'll change colors again. x4 is now located between 1 and 2. Similarly, the value at x4 is lowest, and it's sitting between 1 and 2. So if we were to draw out sort of a picture of this, we would see a curve that goes down there and then shoots back up. Okay? So this means we want to get rid of, we want to retain the first three values and get rid of that last value. So we can do this one last time, maybe in purple. We're now on iteration number 3. We're going to preserve x1 and its value. We're going to now make x2 should be what used to be x4, because that's that next value in that number line. So 1.49. This gave us, I'll put in the extra digits, 1.4903. This gives us negative 1.7714. x3 is now replaced by what used to be x2. So this is 1.505 with a value of negative 1.7691. And then you could do all of the math again to calculate x4. I'm going to cut to the chase a little bit and put in our final values of 1.4256 and that optimal value of negative 1.7757. So what you should hopefully see is using this parabolic interpolation. By that second iteration, we're almost there. We've almost got the same number. By the time we get to our 5th iteration, we have an error that's less than 0.0000, right? Just maybe put 0001, right? We have lots of a lot of this information. So we can, because we're using more information about that local topography. This is going to be the conclusion of the numeric methods that I want to cover for this class. However, I do want to comment very briefly on some built-in MATLAB functions. Namely, there's built-in functions for 1D optimization and multiple dimensional optimization. What we covered earlier today is only been talking about 1D optimization. Oops. So MATLAB has a built-in function called fmin bound. This is going to be for a function. We can put in a function that's going to, we're going to search for an optimum between x1 and x2. So it's sort of like the bracketing method before, where we have to give some sort of range over which to look. Just like before, we can take a function name, so fmin bnd, and then we can call this fmin bound in order to actually have MATLAB solve it for us. So just like any function, we can just put in the function name. So this could be simple, sort of like that. This could be simple, such as f equals at x squared plus exp negative x, for example. Or it could be quite complicated, like that reverse water gas shift equations that we talked about a few lessons ago. So we just put that functioning in there because we're calling a function of a function, and then we put in one of our guesses as a scalar as x. So I don't know, maybe 5 for whatever the function is, and 10, and that will then bound the search. Actually, that's probably a bad choice, maybe 0 and 10. That's then going to bound that search looking for that fmin. So fmin is going to look for the minimum value. This may raise the question, well, what if I want a maximum value? Well, all you need to do is change this f function to be f equals at x negative 1 times, say, x squared plus exp negative x, right? And now all of a sudden, what used to be looking for a maximum has now become looking for a minimum. Many of our searches that we're interested in are not restricted to one dimension. In fact, most problems are looking at highly complex functions that are going to have multiple dependencies. Right? So we often want to look for multiple x's that will give us those behaviors in multiple dimensional space. In this case, we want to use fmin search. This is going to be sort of like fmin bound, except it's going to be able to look at multiple dimensions. It's going to work very similarly, where we just call fmin search, and then we have our function name. In this case, x, though, needs to be an array of values or a vector of values. So depending on how many values we want to look over and try to optimize, we could have, say, x1, x2, x3. In this case, we don't need to bound our solution. We're merely giving it a set of starting values. So maybe if function f is a function of f1 or x1 and x2, we would need to give two function values here. If this function were a function of f1 or x1, x2, x3, then we need to give three starting values. And when we do that, fmin search is going to tell us not only what x1, x2, and x3 are, or sorry, what the value of x1, x2, x3 are that give a minimum to our function, but it'll also return the value of the function at that point. As we go through the rest of this class, we're going to come back to this, particularly when we start looking at optimization functions for complex behavior. So with that, I want to review what we covered today. Hopefully you now have a relatively good understanding of maxima and minima, including the difference between local maxima and minima and global maxima and minima. You know how we can find extrema using the derivative of the function and root finding algorithms. You feel comfortable using the golden search method algorithm. This is sort of akin to bisection, but requires two input points, and then are comfortable with parabolic interpolation, which is somewhat analogous to the false position method, where we try to fit a curve to the function in order to find the maxima. Last point I want to make is, as you've seen through these last few search algorithm procedures, we're required to make a guess. And based on where we make that guess, maxima, a local minima, or at that global maxima. This is one of our problems with all of these optimization searches. We can only find, once we're near an optimum, we're restricted to that area. We're restricted to that catchment zone, right? The optimum finding algorithm, say if we start out here in this place named X, it's going to work to find that optimum. It doesn't know, and it can't know that there's a true optimum sitting, or that the global optimum is sitting all the way out here. All right, I look forward to seeing you in class tomorrow or today, depending on what time you're watching this.